Hey everyone, feeling the pressure for that upcoming stats exam? Take a deep breath. I'm here to be your ultimate study buddy today. We're going to conquer this test by breaking down exactly what you need to know about the shape of data. No fluff, no confusing textbook jargon, just the high-yield, absolutely crucial facts mapped out to help you score top marks. So grab your notes because we are building the ultimate exam cheat sheet.
Here is our game plan for this explainer. We'll hit the core concept of skewness, compare it to dispersion, tackle positive and negative tails, master the mean, median, and mode rules, and finally, look at extreme J-shaped curves. Let's get to it. All right, part 1, the core concept, skewness.
Okay, let's dive into this. We all know that sheer panic of staring at a massive, messy data set during a test. But what exactly is skewness? Simply put, it's the extent of asymmetry, or the lack of symmetry, in how your data is distributed. Basically, if the left side doesn't perfectly mirror the right side, you've got a skewed distribution. It's all about that imbalance. Now, I need you to burn this number into your brain for those tricky multiple-choice questions. 0. If your data is perfectly symmetrical, like a flawless mirror image right down the middle, your skewness is exactly 0. No asymmetry literally means 0 skewness. Simple, right? But examiners love testing it. Moving right along to part 2, skewness versus dispersion.
Listen up, because examiners absolutely love to try and trip you up here. Students mix these two concepts up all the time. Both deal with how data deviates from the center, sure, but dispersion is all about the degree of scatter. Think how much the data is spread out. Skewness, on the other hand, measures the departure from symmetry. Think in what manner it's spread. Dispersion is how much, skewness is in what manner. I definitely write those exact phrases down.
So why do statisticians actually use them? Well, you'd use a measure of dispersion to judge how well your average actually represents the whole data set. If your dispersion is huge, your average might be pretty misleading. But you use skewness to understand the differences between your mean, median, and mode. It immediately tells you if your data is clumping heavily in the higher or the lower values.
And here's a massive high-yield exam detail. In perfectly symmetrical data, your measure of dispersion can actually be any number. The data could be spread incredibly wide from the center. But your measure of skewness, because the data is perfectly symmetrical, that skewness will always be exactly 0. No exceptions.
Okay, part 3, tails, positive and negative.
So we know data can be lopsided, but which way is it leaning? With positive skewness, your frequencies are bunched up in the lower values. Think about real-world wealth. Most of us are concentrated on the lower end of the income scale, right? But a few massive billionaires drag that tail way out to the right. That longer tail points toward the higher values. The golden rule to remember here, the skew is named after the tail, not the clump. Now, what's really interesting here is how negative skewness is the exact opposite. Imagine a ridiculously easy exam. Everyone clumps up in the high grades on the right, leaving this long, sad tail stretching way back to the left for the few really low scores. Since that tail is pointing left toward the negative side of the number line, it creates a left-handed or negative skew.
Bringing us to part 4, mean, median, mode rules.
Okay, focus up. If you remember absolutely nothing else from this explainer, remember this. This is your ultimate exam cheat code. The relationship between your averages is totally dictated by the skew, and it's guaranteed to show up on your test. For a positive skew, that long right tail literally drags the mean up, making it the highest value. The mode is just the peak, so it stays the lowest. So mean is greater than median, which is greater than mode. For a negative skew, totally reversed. The mode is the highest, and the mean gets dragged down the left tail, making it the lowest. So mean is less than median, which is less than mode. And notice how the median is always just chilling right in the middle? That's because it's the physical center of the data, completely immune to those wild outliers pulling on the mean.
All right, pop quiz time. Let's do a quick exam check to test your memory. Imagine you're in the exam hall, the clock is ticking, and you read this question. If the mode is your highest value in a data set, what is your skew? Think about the rules we just drilled.
Nailed it. It's negative skewness. Why? Because in a negative skew, the data clumps at the high end where the peak, the mode, lives, while the mean gets dragged way down by that left tail. Mean is less than median, which is less than mode. Honestly, fantastic job if you caught that logic. Finally, part 5, extreme J-shaped curves. For those of you looking to scrape every single bonus point on the test, You've got to know what happens when skewness goes to the absolute extreme. Let's look at extreme positive skewness. Imagine a curve shaped like a backwards letter J. The frequencies start out at their absolute maximum, right at the lowest values, and then they just steadily fall. A grim but perfect example is mortality rates from childhood diseases, super high at birth, and then dropping off sharply as age increases.
And this brilliantly illustrates the flip side, extreme negative skewness. This one forms a true J shape. The frequencies are incredibly low at the start, and then they continuously climb, hitting their absolute peak right at the very end of the highest values. Think about mortality rates and old age. It's a continuous exponential climb right at the end of the graph.
And that's the whole shebang. Your ultimate cheat sheet is complete. You now know exactly how dispersion scatters your data and how skewness fundamentally shapes it. You've got your positive and negative tails down, and you know those strict mean, median, and mode rules cold. So I'll leave you with this to ponder before test day. The very next time you look at a dataset, whether it's in class or out in the wild, can you immediately spot if it's simply scattered or fundamentally skewed? Keep that analytical eye sharp. Good luck with that exam, and thanks for hanging out with me for this explainer.